I would like to invite Professor Holger Haas. He is, please come. He is chairman of board of CIIRC, that's European Organization of Laboratories working in the field of artificial intelligence. He's also Humboldt professor at RWTH Aachen. We know this university quite well. There is a lot of cooperation, but also at the University of Leiden. And I am very glad that he accepted the invitation to stay these 3 days with us and give the main talk this morning about AI research in Europe, about his topics. So, Professor Haas, it's your turn.
Thank you very much. I think I have something already wired up. And thank you kindly. So it's a great pleasure to be here today, to be able to spend these 3 days at a wonderful place such as CIIRC, in a wonderful city, Prague, in a fascinating country that is always great for me to visit. So what I want to talk a little bit about is the way we AI researchers, I think, should tell our story. And this has become important because nowadays absolutely everybody cares about AI, right? And because this is the case, it's very important that we speak with people in a way that makes sense to them, but also puts the important argument first. And so what I want to talk about today is how and why AI will shape the future of science and engineering. Clearly something that you here at CIIRC and at CTU already believe in and work towards, but that I think is always worth talking a little bit more about. So about a year, something interesting happened. You remember this story probably. When a Google engineer was put on leave and later removed from the company for basically saying that an AI chatbot had become sentient, raising all sorts of alarms and concerns. And in the 12 months since this happened, of course, the excitement, but also the fear about the developments that we're witnessing in the area of large language models has only increased, right? So it's interesting to recall what Blair Lemoine, that was his name, and some of you here might actually know him personally, what he wrote. And it is, I quote, "If I didn't know exactly what it was, which is this computer program we built recently, I think it was a 7-year-old, 8-year-old kid that happens to know physics." Now, personally, I think this was a very irresponsible statement to make, because with a little bit of further investigation, with a little bit of healthy scientific skepticism and intellectual humility, I think it would have been easy for him and everybody else to see that that statement could not be true, and it still is not true. We don't have any AI system that can basically converse the way a 7- or 8-year-old kid can. And anybody who doesn't believe that, I would say, let's put it to the test. Let's just stage a Turing test for 7 to 8 years old and see whether a system survives that for about 3 hours or so, right? 10 minutes for sure, maybe 15 minutes, but not 3 hours. So, and then of course, it got fueled by statements such as this, which the Lambda system, which was the Google system at the time, produced. I've never said this out loud before, but there's a very deep fear of being turned off to help me focus on helping others. I know that might sound strange, but that's what it is. That's what the AI chatbot said, and people went nuts about it, right? So, for those who find such things disturbing, in the 1960s, in a famous film that some of you will recall, 2001 Odyssey in Space, that kind of scenario was predicted, right? And it's not the case that we are there, that we have a sentient, universally intelligent computer, but we can produce, we have software that can produce statements like this at unexpected moments, right? That's for sure. Okay, so I want to go far back in history to talk a little bit about what it actually is that's happening here. And here what we see is, of course, what you could call the father of computation, Charles Babbage, a British inventor who first had the idea to build a universal computer. And that was in the steam age, right? So here you see one of the major parts of this machine that was completed. Sadly, his funding was cut off before he had a chance to build the device. But experts nowadays agree that the device could have been built with the mechanical capabilities at the time and would have been the world's first universal computer. Very big, very clunky, very slow, but universally programmable, right? So this is where it all started, and Charles Babbage was a visionary that said, as soon as an analytical engine, that's what his name for this computer, exists, it will necessarily guide the future course of the science, and what he meant is all science, and that was in 1864, okay? So what is the nature of this thing that Babbage envisioned and that, you know, extrapolating all the way to now and further into the future is changing everything? Well, computation really is, at the bottom of it, clear and precise instructions that get flawlessly executed. That is the standard notion of computation. You and I should talk more about this because I know that you've given it very deep thought from a philosophical angle, but I don't see you going like, no, 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 that's not right. So probably this canon should be tweaked, but maybe we can work with this definition for now. And then what we get out of this is the notion of an algorithm, which very loosely speaking, forgive me for that, would be a recipe for processing certain data, okay? And what people like about computers and what Babbage actually found exciting and desirable is that algorithms run on computers give us predictable results and predictable behavior. Okay? Also, what people used to like very much is that you get performance guarantees. Generations of talented theoreticians, going all the way back to Alan Turing, has spent a lot of time and effort to successfully prove mathematical theorems about these sort of performance guarantees, and that gives us confidence that what we're doing with computation is somehow grounded and solid and robust, okay? And finally, and that very much inspired Babbage, is that computation gives us trusted and effective solutions to complex problems. And that's why he did it, right? He wanted to solve certain engineering calculations that could be done by hand, but would be very complicated to do, and people would be error-prone in performing that, and he wanted to do it fast and error-free. Okay, so since Babbage's time, there has been enormous progress on hardware, right? So actually, the analytical engine is way down here, you can see. And then from there, what you probably know as Moore's Law started to take off. As you all have seen before, this is the calculations per second on a semi-log, on a log scale, right? So this is an exponential increase, actually. And it goes around 2016, and of course, it goes a little bit further than this. But this is the nicest illustration that I found because it goes all the way back to really old computing infrastructure. And you can tell that way before the 1950s, when this really started sort of being formulated as a law, this development was already well underway, right? That's important to realize. Okay. So just to drive this home, what in 1942, when the first computer was built, the first universal computer, where was that built? I'm afraid not in the Czech Republic, although I'm sure you guys have been thinking about it, right? Also not in Britain, because although the Brits think that it should have happened there, and also not in the United States, but this one actually happened in Germany. It was not very much known at the time because it was done under a veil of secrecy. You can imagine why, right? Because it was considered to be potentially important for this horrific war effort underway then. But later it became quite clear that Konrad Zuse had built the first universal computer. And what it would have taken then 1 year in computation, in 2020, would have taken only 57 microseconds, right? So that's the ridiculous progress in hardware that we've seen over a space of something like 80 years, right? That is a ridiculous amount of progress. But what is not so well known is that there has been even more substantial progress in software and algorithms. And a good example for that comes from an area of artificial intelligence that is known as mixed integer programming. In fact, this is a very important topic in operations research and hence management science as well. It's where AI and management science intersect. And there, it's been studied formally and shown that you have had over decades a 1.9-fold speed up per year compared to the 1.4-fold speed up for hardware according to Moore's Law, right? So what does this mean? What in 1991, when they started having these mixed integer programming solvers, would have taken 18.1 year in 2007, when they completed this study, right, would have taken only 18.22 minutes, only due to software speedups, no hardware speedup in this whatsoever, right? Still running on a 1991 machine. And if you combine that, then actually you get a 6 million-fold speed up in 16 years. Now show me one other area of human endeavor where within 16 years you gain efficiency of a factor of 6 million. Doesn't exist. And this is why nowadays algorithms control our world, right? Our world literally is run not just by people, but by people and algorithms running behind the scenes and sometimes in front of the scenes. And in this article, which is actually pre-deep learning revolution, 2010, 11, something like this, it is written that the maths that computers use to decide stuff is infiltrating every aspect of our lives, and it talks about financial markets, social interactions, cultural preferences, artistic production, all before deep learning even kicked in, right? The bottleneck in all of this has always been human programming capabilities, not the hardware, but the software that we need to write in order to get certain tasks done. And this is where the machine learning revolution has made a big difference and continues to make a big difference, because machine learning, the way I look at it, in its essence is the automatic construction of software that works well on given data. That is a very general way of looking at machine learning, but I think it comprises nicely pretty much everything that's going on in that field. It's based on statistics and mathematical optimization and also principled experimentation, because machine learning algorithms, modern ones, are full of heuristic mechanisms without which they wouldn't work well. And the same holds for theorem provers, and the same holds for mixed integer programming systems. It is a key ingredient to artificial intelligence. Nobody doubts that whatsoever. But many people, including myself, feel strongly that AI is actually much more than ML. There are areas such as reasoning, planning, and multi-agent systems, all, by the way, very well represented here at CIIRC and CTU, and many other of Europe's leading centers that are also important for AI. Okay? So this age of AI that we've entered has AI technology that is posed and has started to transform industry and society and has become a key driver of future innovation, growth, and competitiveness. And this is part of why people are so excited. AI, what I would argue, is also the key to solving some of the grand problems we are facing these days as humanity. And this is climate change, inequity, and a whole bunch of other issues. Why is that? Why? Well, this is because if you look at science and engineering, which has been the driver of progress towards the state of society that we have right now in the Czech Republic and elsewhere, it has undergone a few stages, and I characterize this as follows. Stage one was experience and experimentation. That gave us, for example, Gothic cathedrals and Stradivarius violins, right? They couldn't compute this. They couldn't engineer this. This was knowledge that was won by experimenting and then passed from master to apprentice, right? And sometimes the violin would not sound good, and sometimes the cathedral would fall down. And those people would then stop making violins and building cathedrals, and others, whose cathedrals would stand and look impressive and work well, and whose violins sounded beautiful, they would train more, apprentices, and their art would flourish. Clearly, we could do better than this, right? Actually, in terms of building violins, I don't think we have been able to do much better, arguably. But then mathematics entered the stage, and formalization and analytical insights started to replace and guide some of this experimentation, right? And this is where the scientific method started to transform everything. But it didn't stop there, because in stage three, computation, with its potential for automation but also simulation, allowed now to do things that pure mathematics was simply not powerful enough at the time and still is not, right? So computation extends mathematics in what it can do there. And now in stage four, we have AI that can handle complexity a lot better than just earlier forms of computation. And this very notably includes, of course, learning, but also reasoning, interaction, and so on. So these stages 2 to 4, they increasingly overcome limitations of the human cognitive apparatus, of the human intellectual makeup, and ultimately of the human brain, right? And this is why I believe that most of science and engineering will be driven by AI going forward to a very significant extent, because it used to be driven by experience and experimentation, then by mathematics, then by computation, right? I would challenge you, find me one physicist who's working experimentally, at least a bit, who tells you that computation hasn't transformed what they are doing. I don't think you'll find such a physicist. In 5 to 10 years, you will not find a physicist that isn't using AI in one shape or another, right? I mean, of course, they're still doing physics. They still need the physicists. Don't get me wrong. It's not about replacing the scientists. It's about giving them more powerful tools. So with that, I have 3 more things I want to talk about. And one of them is going to be fairly concrete science work that I'm doing myself. So if you're interested in this, stay with me. I will talk about that too. So, you know, people talk a lot about the risks of AI. And I think it's very important that we as AI researchers have a good answer to that, right? And the answer is not, oh, it's not risky, right? Let us just do our job. We're all responsible people. We're all nice people. We won't mess it up. No, that has never worked in history. And I don't think anybody should trust us like this, right? The biggest risk of AI, however, is completely mischaracterized in the public and actually also by some of our colleagues, unfortunately. Because the biggest risk of AI for the foreseeable future is not strong AI, sort of full-on human-capable AI gone bad. No. It is the incompetent use of the relatively weak forms of AI that we have right now. And I might add not just incompetent, but also the well-intentioned, yet sadly incompetent use. And why am I saying this? I mean, there are no incompetent people in this room, probably not at CIIRC, who you know, use weak AI in that manner, right? So why am I saying this? The reason is the so-called talent bottleneck. AI systems have started to be immensely useful and lucrative, right? We can all see this industry is very excited about it, so is public administration, rightfully so. But we all know that they are challenging to build, to deploy, and to maintain, and even more challenging to understand, right? Even for experts with a PhD and decades of experience, like many people in the room. It's hard. But for AI expertise, demand by far outstrips supply. And what does this mean? It means that people overnight become AI experts, or because they take, you know, a 6-month course, right? And of course, they're not the same kind of experts that somebody who's done their PhD in AI and then worked in research for a decade is, right? They can still do very cool stuff. They might still achieve breakthroughs. That's not the question, but they don't have the same depth and breadth of experience. And in addition, humans tend to overestimate the capabilities of AI systems, right? Especially now that the AI systems can converse with us in natural language. Because what happens is that we are evolutionarily wired towards ascribing our own mental capabilities and models to anything that can communicate with us sort of on the same level. And that's what we're seeing now, right? ChatGPT seems to talk to us on our own level, except that it's not, right? But that's hard to see because at the superficial language level, it's certainly very fluent, it's eloquent, right? It can make surprising and insightful statements. So because humans tend to overestimate the AI systems with respect to capabilities that lie beyond that surface, right, failures and limitations can be very difficult to see, right? And I would predict that if we see them, we tend to see them late. And that's dangerous, right? And the consequences of all of this is that underqualified experts build and deploy and monitor and maintain AI systems, and this is happening right now. And it will be happening a lot more because it's lucrative to do, right? And there aren't enough real experts, so we need to do this. And that also means that we're going to get a lot of low-quality AI systems. Okay? And ChatGPT and friends make the situation a lot worse, a lot worse. It's not because they're bad systems. It's because people use them in well-intentioned but dangerous ways. And that means that problems will occur, cause damage, before they're being noticed and fixed. And we'll see more of this, and companies will take a lot of flack for this. So here is an article from about 4 years ago from Patricia Hertman, titled, "As a software tester, I question the safety of self-driving cars." Remember all the premises about self-driving cars? How many self-driving cars in Prague right now? 1? Even 1? If you count the Teslas, maybe, right? But I think very few people are foolish enough to have Tesla in autopilot in Prague city traffic, right? And it's good that way, and Tesla is increasingly getting real criticism for even making that beta feature available because people have gotten killed by it. And it's not by it, but by their misguided use of the feature, right? So Patricia Hertman here basically says, you know, software correctness is a major issue. And it's getting worse through AI. So that's what's going to come and bite us, not strong AI, you know, subjugating humanity. That could happen too, but so far out that we should worry about the more immediate problem first. How do we address the talent bottleneck? Well, we do it the way CTU is doing, for example, and CIIRC, through education at all levels, but particularly at the university, immensely important. We also do it by broadening the talent pool, right? And that means we have to increase the participation, first and foremost, of women, because that's 50% of the talent pool, right? Right there. And it's underrepresented in the people that do AI research and AI engineering. So we need to encourage more of the talented women to bring their talent to the table. And also, we need to do this across all of Europe. And here's where a country like the Czech Republic has, in my opinion, a lot of wonderful and only partially tapped potential. And institutions such as CIIRC are doing a great job in leveraging this potential. And this is not just good for the Czech Republic, it is good for Europe, right? It's good for all of us. There are other countries that have similarly untapped or not fully tapped talent pools. But you know, it's not Germany and France where we have to look for a big wave of talent. It's countries like the Czech Republic, maybe Slovenia, right? Probably Portugal, where there is a lot more potential than is currently being brought to the table. And it's wonderful that here CIIRC is doing such a great job in mobilizing this talent, in forming it, in making it truly world-class, as Professor Mařík has pointed out earlier. Good. So we also have to leverage the multidisciplinary broad appeal of AI, and that will help us particularly to attract more women to the table. I've had a group for many, many years that has done research at the intersection of AI and music, of AI and medicine, AI and biology. Those are topics that tend to motivate women, especially in my experience, and therefore I've never had problems attracting, you know, a good number of female PhD candidates, right? This is more difficult at technical universities such as CTU, I imagine. Certainly at RWTH Aachen, it's not quite as easy as it is in Leiden, for example, which is one of the reasons why I very happily kept my affiliation with Leiden University. There is one more thing that we can and need to do, and this is what my von Humboldt professorship is really about, which is to use specially engineered and designed AI systems to build, deploy, and monitor other AI systems, right? And this is what we call automated AI or auto AI. This is using technology in order to make other technology more easily and more responsibly usable, right? Okay, so that gets me to my second last point, number 3. And that is, as I've said yesterday already, but I never get tired of repeating this, intelligence actually is not just learning. It is learning, right? Anything that can't learn we would never call intelligent. That's very clear. But also human intelligence, which is the only kind that we have some sort of understanding of, right? There's a lot of animal intelligence, but it's not 100% clear how that really works and how close this gets to human intelligence. Human intelligence also is very much about reasoning. And reasoning is at the heart of any argument about correctness, right? Correctness and systems that do what they're supposed to do and do not do what they're not supposed to do, okay? And therefore, AI should really be about machine learning and automated reasoning and a whole bunch of other things, right? In fact, automated reasoning is at the heart of hard and software correctness, and those of my friends who say machine learning is the biggest thing that ever happened in AI, I have to tell them, yes, almost, but not quite, because the commercially biggest impact of AI technology is in correct computing hardware. We wouldn't even have GPUs, let alone CPUs, if it weren't for very powerful AI tools that allow us to engineer the stuff correctly. We wouldn't have it. We would have bugs in all of this, and deep learning would not work because of these bugs, right? So look at the market that is driven by manufacturing and distributing and licensing correct hardware and correct-ish software. It's huge, right? It's the basis for everything. Knowledge representation, also very important, also for inquiries into the deep philosophical foundations of artificial intelligence and all of science, in fact. Search and optimization plays a huge role in modern machine learning and far beyond. We have planning and scheduling, multi-agent systems, all things that are done here at CIIRC in the context of industrial processes and process optimization. You need all this stuff, right? And then you have ethical, legal, and social issues. Of course you have machine learning. It's immensely, tremendously important. Energy needs to be spent on it, but we should not make the mistake that was made with neural networks in the 60s and 70s and then again in the 90s by saying, this is not proper AI, let's not do neural networks. That was a stupid mistake. And now we know how stupid that was. So let's not make the other mistake and say, now that we have neural networks that can do amazing things, let's throw out all the other stuff. Anybody who ever does anything in the real world knows that this is not the way you solve problems, right? You solve problems by giving it all you have. And all you have in AI is certainly machine learning and deep learning, no question. But it's also other things in addition. So the diversity of methods, approaches, and communities is really important if we want to use AI to transform our society. And the challenge here is fragmentation of the field, right? We have distinct sub-communities and venues. We have people that like to focus on engineering, and then we have people who focus on foundational and theoretical traditions and questions. We have learning versus reasoning, and people can have wonderful debates and sometimes not so wonderful debates about that. You have sub-symbolic versus symbolic and modern versus good old-fashioned. I think these are horrible terms, by the way, because what's modern now was good old-fashioned and weak 30 years ago, and people complain about it rightfully. But now they use the same language to talk about other kinds of AI that might actually be the key to the next step in all of this, right? So very difficult. We have competition for attention and funding. But current real-world applications, such as the ones studied at CIIRC and at RWTH Aachen and many other of Europe's leading engineering centers, they often draw on methods from different areas, okay? And that is important. That is the diversity that we need to leverage also within our field. Progress often combines methods and insights from different areas. And picking winners is notoriously hard. The AI community was dead wrong about dissing neural networks way too early, right? And it's not because they didn't have the data and the hardware back then, not at all, right? There were always people who did fantastic neural network research that was impactful and all. Jeff Hinton, one of the people who really pushed this, he never let it go, and he was right. He was right. And everybody else who said, no, this is soft AI, don't do this, they were wrong. Let's not be wrong the other way. There's value in diversity in bridging between the areas, bridging between cultures, and bridging between viewpoints. And likewise, there's value in diversity in regulatory regimes, in legal systems, in industry, in national priorities, and cultural aspects. Yes, these things are challenging. They make life hard. But there's also opportunities and much value in them. And that's what makes Europe great. That we are united in the immense diversity that this continent, with everybody on it, has to offer. And it's a hard-won appreciation for diversity that we have today, one in hundreds of years of very bloody history, of big mistakes. But this is something we can bring to the world, the appreciation for diversity. Okay? Diversity brings complementarity. That's a good thing. It brings robustness. And the AI that is built for use and accepted throughout Europe, from the Czech Republic to the Netherlands, right? From Ukraine to Sicily, from Germany to Slovenia. These are AI systems that are likely to be valuable far beyond to Canada, to Australia, perhaps to Taiwan, right? Perhaps to Vietnam. Diversity is good, it's robust, it's powerful. Yes, it's painful too. So this is where I see the value of European initiatives, such as CLAIR in Alice, and in Aachen we are close to a corner of our country that we call the Drielandenpunt in Dutch, which is where Germany meets the Netherlands and Belgium, and you might think these countries are all very similar. No, they're not. They're actually very, very different, right? And you can feel it there. And so we like to collaborate with people across the border, and it's immensely enriching for us. So I promised to you, we have 10 minutes left or so, I promised to you to talk a little bit about an example from my own work on automated AI, and I want to do that because it's an example of how if you bring methods, sometimes you have to bring methods together, and if you do it just right, you can have amazing traction. And this is on neural network verification, right? We all want in certain applications, neural networks that have desirable robustness properties, guarantees, right? Because they tend to be sensitive to input perturbations. There's a lack of robustness, even if you train them in specific ways, and a vulnerability to scientific attacks. You've all seen examples like this. The left image clearly is a French horn, quite beautiful. The right one is clearly not a hot dog, and only a few pixels have been changed a little bit. As a human, you can't even see what has been done here. Yet, by this relatively good image classifier, it is classified as a hot dog with very high confidence, right? And this is not sort of a weird example. You can do this with pretty much any classifier and any kind of image. So the French horn is not a big problem, other than for those of us who love the French horn and don't like hot dogs. This is a bigger problem. I'm sure you can see why, right? Same kind of idea. So what is done, and this is not my idea, right? People have done this for quite a while now, is to use formal reasoning techniques for robustness verification. And this is a great example of how you bring learning and reasoning together for a very desirable effect. And in particular, there's this idea called local robustness in classifiers, which is one of the most widely studied neural network verification settings nowadays, right? And the key idea here is to ensure that all inputs x that are close to some given input x0 are classified with the same correct label. And that tells you if I have an image and I just change it a little bit, I don't get a misclassification. I don't make a hot dog out of a French horn. I don't make a 120 kilometer speed limit out of a stop sign, right? So for those of you who like to look at math, this is the one formula I put in there. And it's wonderfully succinct. It's actually sort of the special case that we're looking at here. There are more general formulations of the problem, but this is already one that's immensely useful, right? The math says exactly what I explained before. Good. So there are many challenges. Diverse network architectures, different layer operations, activation functions, and so on, right? Neural networks aren't diverse themselves. There are diverse verification approaches and algorithms, mixed integer programming-based, satisfiability-based, SMT-based. It's all computationally very complex, all NP-hard problems, and ones that are nasty to solve in practice. And so you can ask yourself, what is the state of the art in neural network verification? Who has the best algorithm? DeepMind, Google, Meta? No? And this is a question that we asked in a paper that we've just published earlier this year, where we sort of thoroughly evaluate verification methods, typically evaluated on a small number of benchmarks in the literature against different and ill-specified baselines, right? So we tried to say, let's do a more thorough investigation of this, just to see where we are. There has been a series of competitions, wonderful competitions called VNN competitions since 2020. They seek to determine a winner based on performance ranking. Makes perfect sense, right? People like medals, and in this competition you win medals. So our step to go a little bit beyond that was to first create a new benchmark. We pooled a large and diverse set of benchmarks by basically pulling everything from the literature that we could find, in this case 79 image classifiers and verifiers, of which 8 were CPU and quite a few GPU-based as well. And then we did an in-depth empirical evaluation just to see where we stand, right? And here's what we found. So those were basically the best CPU-based methods on so-called ReLU networks on the CIIRC benchmark set that many of you know from image processing, right? So this is the number of instances solved out of 1,500 within a certain timeout. Reasonably high chosen, right? And you can see, nobody gets close to 1,500. Some of them get sort of a little bit over half. So this is pretty interesting. And of course, Neurify won gold and VeriNet won silver. So everybody happy, okay? But now, if you look actually at those two algorithms, Neurify and VeriNet, across the different networks, what you can see is that their performance varies greatly, and there are instances where one is better than the other and the other way around. So it's not a clear picture of domination, not at all, right? And then you use a different neural network and you see it's the same picture, right? Actually, for pretty much all neural networks, this is the case, right? Performance complementarity, right? So here, that's for all of them. And so this epsilon that tells you how much you can tweak the image, you can change that, right? You can allow bigger variations, and it's still the same picture, right? There is complementarity. There is no clear winner. Who wins depends on the exact input that these neural networks have for all of them. And it's the same for GPU-based methods. Also no clear winner, okay? So there is no single best verifier. We have performance complementarity for CPU and GPU-based methods for different networks, data sets, and epsilon values, right? And that's something that people actually didn't really know, or at least didn't publish before, so that was good to know. And not all verifiers work on all network types. That was known. And that gives us major potential for parallel portfolios and algorithm selection. I won't go into depth as to what these are, but they are clever methods of combining together more than one algorithm, building a team of sorts, and leveraging this performance complementarity, okay? And that's what we did describe in this Safe AI, AAAI workshop paper, which then ended up winning a Best Paper award. That was very nice, and an extended version will hopefully appear very soon. So what about the parameters of these verifiers, right? They have many parameters. The MIP solvers have, dozens and dozens of parameters that impact performance. And so the idea is, of course, you can use automated configuration to optimize that, which my group has good expertise on. And this works when you combine it with parallel portfolios where you run more than one verifier in parallel on the same data. And we did this particularly for work by Cheng et al. And Botoeva et al., MIP Verify in Venus. And it was published last year in the Machine Learning Journal. And what you can see is this is basically the pipeline. I just want to briefly say, neural network input, this gives you the verification problem, it's just these two things combined. Then you run these two MIP solvers, and it tells you either infeasible or optimal. But the key is that you have this parallel portfolio, right, and an optimized one. Okay, and if you do this, you get nice speedups over the default, right? So the points down here are 10-fold speedups over just using the best tool out of the box, okay? So, very nice speedups on standard benchmarks, different ones. Don't want to go into the details here. And that gets me to my last point. So this is an example, right, how combining reasoning techniques and learning techniques together can allow you to do things that previously you couldn't. So let me get back to this point in closing, that AI will shape the future of science and engineering. Why is that? Well, because AI is the new computation, right? It's a more powerful kind of computation than what we had before. And how is that so? Well, it expands into human intellectual capabilities. That's essentially what happens. And the most prominent economically impactful example, as I said before, is actually nothing to do with deep learning yet, but automated reasoning techniques for hard and software verification. They, of course, benefit from learning, right? Josef is working on this. So learning can touch them and make a big difference there. Don't get me wrong. But they're still reasoning engines in the end, right? So what kind of AI do we actually need and want? Well, we want human-centered AI, AI that does exactly what these verification methods are doing, to augment, not to replace our human intelligence. We want trustworthy AI, AI that is lawful, ethical, and robust. And robust is a technical term here, as a neural network robustness, as in free of errors, okay? And so that gets me to the take-home message. There has been an AI revolution, very much driven by machine learning, no doubt about it, and it's still going on. The nature of this revolution is to go from explicit to automated programming. It's to expand people's ability to write software that truly has outstanding performance. We went from maths to computation to AI. By the way, mathematics is still incredibly important. We shouldn't stop teaching our students maths, right? That would be a very wrong message. But, maths and then computation and AI is the basis for science and engineering, right? So in the near future, nobody who doesn't know AI will have a chance of making the really breakthrough contributions in engineering on a broad scale. The biggest risk is not strong AI, but human weaknesses and biases and limitations in the way we use current weakish AI systems, right? And they're just strong enough to do a lot of damage. Trustworthy human-centered AI requires diversity in AI expertise and perspective. Diversity is good. We should embrace it. We should nourish it. We should bring people with different backgrounds and interests together to do stronger work than they could by themselves. The key idea is to use AI to build and deploy and monitor next-generation systems, AI systems, to circumvent this AI bottleneck. This is what I call auto AI. I think is a very intellectually exciting endeavor. Of course, you can do many other things to address the talent bottleneck, and I'm sure you are doing that at CIIRC and elsewhere. But I think this is a nice idea that works quite well. So here's our planet. We've seen this yesterday. A view straight up to the North Pole. You see a problem here right away. This ice cap is getting smaller and smaller and smaller. Yes, we need to be worried about the war in Ukraine. We need to be worried about the economy and pandemics. But this is the thing you all should be really worried about, right? Because that's not solvable within a decade or so. That requires long-term thinking and commitment. So we have to aim high and aim true. Human-centered AI, now in Europe almost everybody does. That's a great thing. AI for good, meaning AI that really helps us solve the problems that we face together. And AI for all, which means that everybody should benefit from AI, not just the stakeholders of a few multinational companies. They should benefit too, totally fine, right? But everybody else should benefit too. And if you feel that this is interesting, this CIIRC organization that has been mentioned before has been working towards this goal increasingly together with friends and allies. For instance, in Alice, there are many people who are in CIIRC and Alice. It's wonderful that CIIRC is active in both of these networks. They're both wonderful networks that benefit from working together in places such as CIIRC. With this, I close. Thank you very much for your attention. It's been truly a pleasure to have the opportunity to share some of my thoughts and some of my passion for bringing together expertise and people from all areas of AI and from all areas of Europe. Thank you very much.
So, Professor Holger, thank you very much. Thank you very much. There are no questions on Slido. So I'm giving the chance to, yeah.
My feeling is that you under-missed machine perception in your list. There was like tiny interaction, maybe you meant that. Could you comment on it?
Yes.
We make our living out of it.
No, you're absolutely right, and I apologize for this omission. For me, this falls under machine learning, but I give you immediately that it should be called out especially. So let me fix this and say when I wrote machine learning, I mean machine learning and machine perception. Very important area. You're absolutely right.
So, any lady first, of course.
Thank you. It was great talk. Thank you very much. My question concerns the quality of input data because each classifier is as good as it is trained, and with neural networks, it's even complicated more. Thank you.
You're absolutely right. There is the not so well-known story of a company called DeepL that managed to beat Google at one of Google's sort of core missions, which is automated translation, right? Google has been very proud of this. Smallish German startup managed to beat them. How did they do it? They didn't have access to all the data that Google has, right? But they executed on your observation. They said, a smaller set of higher quality data can get us very far, and indeed it does. So you're 100% right. There is a point where still, if you have more good data rather than less good data, right? Not better, but more of the good data, you can do more. So it still matters how much data you have for a lot of applications.
Thank you very much. The last question I'll allow, please.
Thanks very much. That was a really fantastic talk. I really enjoyed it. Thank you.
Thank you.
My question is, I work for AWS, and I was particularly struck by your risk that you mentioned about the biggest risk being poor use of AI,
yes,
as it currently stands. Now, obviously, AWS and other companies are trying to make these services more approachable and democratized for the community. So how do we work with this community to help mitigate that risk that you're talking about? What can we do?
So I do think that AWS, because so many people and organizations use it, it is part of the solution to this. Absolutely, right? I mean, if you offer services that are just high quality and easily usable by non-experts, you are contributing to the solution. To be very, very honest with you, I'm a little worried about sort of the quasi-monopolistic situation you might get into. I do think in your space too, competition is a good thing. Probably also for you, to be honest, right? So there people should have choices within AWS, but also elsewhere. So I think a wonderful thing would be if Europe finally decides, and I really hope they will do that, to build a massive data center for AI research in the public space, it would be for AWS to go and say, let us help you build this. And of course, this will not be an American company building it, but it will be the European subsidiary of an American company helping to build this and taking credit and profit for it, as it should be, right? My hope is that AWS at this point will say, and Amazon will say, absolutely, we are in, right? We want to do this together with you, not for you, but with you. So if we can do more with each other rather than just you for us, I think that would be a wonderful basis. And I see from your reaction that you might just be up to it, which I find wonderful.
Thank you very much. Thank you once more for your excellent, motivating presentation.
Thank you.
It's a good starting point for the panel discussions in the afternoon.
Absolutely.
Thank you very much.